Good evening, everyone. It's my pleasant duty this evening to welcome all of you to this event. This is an event that's jointly conducted by TiE Chennai, NASSCOM, and the Internet Society. I see many TiE members, governing council members, participants, etc. Welcome to all of you. This is one of those very important events. We've been having a few of those recently in TiE. The last time we were here was to listen to Kanwal Reiki, the original entrepreneur, the founder of the TiE network. He spent an evening with charter members of TiE. That was in association with the Madras Management Association. Today we are happy to collaborate with NASSCOM, Internet Society. Sivasubramanian from Internet Society is here. Ramaraj is here, the past president. He has just come here after successfully completing TiECon, the annual conference of TiE Chennai in December. Let me welcome all of you, and a special welcome to Dr. Vint Cerf, who's been here. Many other people. I was at a meeting in the adjoining hotel. There are about 3 or 4 people who immediately recognized him. So I asked them, wow, you know about Dr. Cerf. He's saying, we've been attending his events in IIT yesterday. We were with him today in the meeting. And I'm sure they are going to come and listen to him again this evening. So they're all fascinated by your lectures. Thank you for being here. Let me conclude by welcoming once again and leave it back to Praveen. Thank you.
Thank you, Lakshmi. May I now invite Mr. Sivasubramanian, President of Internet Society India, Chennai Chapter.
Good evening. And Internet Society India Chennai Chapter is one of the 90 chapters of the Internet Society. And at the Internet Society, we have chapters and over 55,000 members. And Internet Society is home to Internet Society is home to the Internet technical community, also to the Internet Engineering Task Force, Internet Architecture Board, and most of the standards for Internet is developed through these bodies by an open process. And the Internet Society works very closely with ICANN and W3C. And at the Internet Society India Chennai chapter, we contribute to the Internet governance policy making process and take part in international forums related to Internet policy and technical development. We have, from the Internet Society, we have always wanted to have a program with TIE for a very long time, and it has happened with the visit of Dr. Cerf. And the topic chosen is with the purpose of asking Dr. Cerf to tell us how to build a Google or a Facebook from India, and to tell us that we don't need anybody's permission to do that. We don't need licenses to do that. That is what the internet ecosystem is all about. And also to ask you to take part in the policy process, to provide inputs to governments to join the Internet Society, to make sure that this environment of permissionless innovation is preserved for us to prosper. And I'm enormously grateful to Dr. Cerf for setting aside his time to take part in this meeting. And he has been very kind. And we are also thankful to TIE. Though it's a joint meeting, most of the work has been done by TIE. As also the sponsorships, virtually everything was done by TIE. Thank you very much.
Thank you, Shiva. It's my pleasure now to invite Ramaraj, past president of TiE Chennai, also an advisor to the Internet Society, to introduce Dr. Vint Cerf.
Vint Cerf is known as one of the fathers of the Internet. He is currently the Internet evangelist, and rightly so, because not only did he create the Internet, but since then he's been traveling around the world to ensure that there is a benevolent environment in which the Internet can grow and flourish. And so that is really what Vint has been doing all these years. 44 years now since the Internet was invented by Vint and a few of his fellow scientists at UCLA. At the 44th year, internet is something that we take for granted. It is ubiquitous. It is there. So much so that some countries are saying that access to the internet should be a fundamental right and actually have made it so. Our Ministry of IT is considering that in new buildings, as part of the completion certificate, along with other utilities of electricity, water, etc., access to the internet is going to be one of the things that will be mandated in new buildings. So it's becoming more and more core to what is happening in our lives. I just thought I'll touch upon a few issues and crossroads I think we are at. The first is there are about 2 billion internet users, about 140 million or so are from India. Many of them access this using the mobile. But there are another 4 to 5 billion who need to get included. So one of the initiatives that Vint did many years ago, which is bearing fruit, is the starting of what is called internationalized domain names, or IDNs. We have .in in India. That is now available, or will be available shortly, in 8 local scripts. That is in Hindi, Tamil, as .bharat, Bharatam in Tamil, etc. In 8 native local scripts, it's going to be available as a starting point to bring people, non-English speaking people, onto the net. Similarly, it's gone into Arabia, China, Russia in local language. It's something that Vint started, and it is a starting point for how to get more people onto the internet. The second big initiative that was started, which is now again starting to bear fruit, is IPv6. IPv6, Vint is the honorary chairman of the IPv6 forum. And IPv6 is something that is going to make Internet of Things a reality. We are starting to see it already in the mobile phones, but we are seeing it in almost everything, cars, trucks. And IPv6, those numbers are now available compared to IPv4, almost limitless in relative terms. So it is again something where we are going to see a serious impact in the way we think and use the internet going forward. A third area that is starting to impact is internet governance. Vint helped start an organization called ICANN, which is a not-for-profit organization out of California. It's an organization that focuses on internet resources, names and numbers. Names like .com, .org, .in, etc., .bharat, and IP addresses. That's one or a couple of those resources. This was started, and I had the good fortune of being on the board at ICANN when Vint was the chairman. And there, ICANN was started keeping the fact that it's a multi-stakeholder model. All of us can be part of internet governance in the ICANN model. It's got civil society, it's got technology people, it's got lawyers, copyright lawyers, trademark lawyers, it's got governments. So it was multi-stakeholder, light touch governance. But with the internet becoming more and more influential, with events like the Arab Spring, there is a move to see how the internet governance can be more tightly influenced by the government. And I think part of what we're talking here of an open internet is how can we all participate in making sure that this light touch multi-stakeholder model carries on. So that's something, and it so happened that ICANN, and with a few influencers like Vint, spoke to Kapil Sibal and some of our Ministry of IT folks who had a position saying it is good for the internet to have government say globally. And luckily they changed that and have now taken the stance that it should be multi-stakeholder driven. And they said that at the IGF, where they said it should be multi-stakeholder model. This is the way inclusion will happen. This is the way innovation will happen. And that's something that came out, luckily for us, that India has had the foresight to participate in that. I think the last one I wanted to touch upon is internet regulation. Internet regulation is again coming up where people want to start controlling content and behavior. We've had stark example of two girls who said something on Facebook and were arrested. If they had written to the editor of Times of India, instead of going on to Facebook, offline media, would the police have arrested them or would somebody have sued them? So the due process of law for offline is getting accelerated, exaggerated in the online world. And therefore, how can we bring some sanity? It's work in progress. People don't know how to respond to something that creates this level of impact. And so how can we all participate in making sure? So January 18th last year, there was a bill that was going to be passed in the United States that would have in some way brought a degree of censorship to the internet. More than 10 million people rallied around and got their both online, offline support to say this is rubbish, it should not happen. And it was actually called the dark, many websites went dark. And it has now been stated as Freedom Day for the internet. So January 18, just a few days ago, was celebrated as the Freedom Day for the internet because the government of the United States said we will now rethink that bill. And therefore, that kind of censorship is not happening. How can we participate? And ICANN and other bodies, ISOC, which Shiva was talking about, are bodies in which we can all participate and actually influence, because multi-stakeholder model means internet users to technical standards, to policy, government, all of that, and we can actually participate. And if you go to the ICANN.org site, that's one place where you could participate, or ISOC, Shiva is here, you could talk to him. Let me come to introducing the speaker, which is really my task, but I thought I'll bring it in context of why we are so excited by the presence of Vint, who not only helped invent this fantastic tool that we use, but has also worked very hard to evangelize the internet and see that there is a safe harbor for us all to use it. Many pages of awards, so I won't go into all of them. I'll just highlight a few. Vint. In 1997, President Clinton awarded the US National Medal for Technology. In 2004, the Alan M. Turing Award was given to Vint, which is considered to be the Nobel Prize of Computer Science. It's a very unique prize that was given. President Bush gave the Presidential Medal of Freedom. It's equivalent to a Bharat Ratna. It's the highest civilian award that can be given, that was given. There was the Japan Prize, extraordinarily prestigious recognition from Japan. The National Inventors Hall of Fame have inducted Vint for all the innovation that he's done. The Stanford Engineering School calls him a hero in that engineering school. He was chairman and founder of, helped found ICANN, founding president of ISOC. On January 16th, President Obama invited Vint to join the board of directors of the National Science Foundation. This is a governing body for all science and technology in the United States, including engineering and science education. So these are just a few sample of the kind of awards and recognition that Vint has had. There's one other aspect to Vint that I enjoyed as on the board. Outside of the internet, he loves fine wine. And one of the benefits we all had was great wine when Vint was around. So Vint, thank you for that, and we all look forward to hearing to you. The stage is yours. Vint.
Well, first of all, I really appreciate an opportunity to speak with you, particularly considering that many of you are part of the entrepreneurial business community, and if there is any place where internet can be leveraged, it's in your hands. I did want to mention a couple of, Ramaraj, actually you covered a good deal of material that I would have covered in my talk, so actually I appreciate that. It saves me the trouble, and I'll be able to emphasize other things. With regard to anniversaries, though, I would like to mention a couple of them. The Internet Society was started in 1992 on January 1st, so it had its 20th anniversary last year, and we celebrated that in Geneva with a big party. This year, on January 1st, the Internet itself was actually turned on, it was 30 years ago. It's not quite, I'll come back to the 44 number in just a moment, but on January 1st, 1983, we turned the Internet on, and it's never been shut down since that time. Around September of 1973, 10 years before, Bob Kahn and I wrote the first design specification for the Internet. It was published in the IEEE Transactions on Communications in May of 1974. So around September of this year, Bob and I will celebrate the 40th anniversary of the design of the Internet. Now, the 44 number that you mentioned actually goes back before Internet to a U.S. Defense Department project called ARPANET. ARPA was the Advanced Research Projects Agency. It was created by President Eisenhower after the launch of the Sputnik in October of 1957. The U.S. response to that was sort of shock, gasp, oh, now how could this possibly happen? So the president created the Advanced Research Projects Agency to make sure we wouldn't be surprised again like that. And among the first things that ARPA was responsible for was getting the U.S. into space. Eventually that transferred over to NASA. And so the ARPA group started focusing on other things, including command and control and the use of computers in that domain. So the ARPANET project was in fact the first big experiment in packet switching. So we built this network, deployed it across the U.S. in a number of universities, maybe a dozen or so universities and several military installations, and demonstrated that packet switching could work in an interactive mode, whereas most telecom engineers at the time were accustomed to circuit switching and didn't believe that packet switching could possibly work. AT&T had no interest whatsoever in this technology. They said it wouldn't work, but they would be happy to lease telephone circuits to us so we could build our stupid network. So we did. We built the ARPANET in 1969. That's where the 44 number comes from. But it had been in operation for 4 years when Bob and I decided it was time to look at what happens when we have different kinds of packet switch nets, mobile radio, shared satellite channels, in addition to the ARPANET was built on dedicated wireline connectivity. And so the question was, how do we interconnect all these different networks together? And the solution to that problem was the set of protocols called TCP/IP, which Bob and I developed in 1973. So that's a little bit of history and why this year has turned out to be a celebratory one for many of us. I would like to suggest to you that all of those objectives that Ramaraj so well expressed should suggest to you that you should be members of several organizations. TiE, obviously, here you are. But think about the Association for Computer Machinery, which is a global organization which has a big footprint now in ACM India. We just celebrated 3 days worth of activity at the IIT Madras campus. That organization was created in 1947. I have the honor of serving as president of the ACM for the next couple of years, and then past president for another 2 years. You can also join the Internet Society because it's turning out to be a very important avenue for conveying policy positions that would try to preserve the openness of the Internet. And so if you don't have enough organizations to be members of, you could consider joining ACM and ISOC as well. And I want to go on record as thanking you, Ramaraj, for service on the ICANN board. This is a very, very important organization. And I can tell you that his advice and counsel was invaluable and continues to be very much valued by the leadership there. So let me now turn to the topic of the evening, which is keeping the Internet open and as universally accessible as possible, because it's an opportunity and an avenue to create GDP growth and to create real wealth. But in order to understand that, we have to look at some of the statistics that are associated with this network. In the middle, or at September of last year, the estimate of the number of computers that were visible on the network publicly was slightly under 1 billion, 900 and some odd million machines. But that does not count all of the machines that are hiding behind firewalls. So at Google, for example, we have a very, very large number of machines. They are not seen by any of the users as individual servers. They're seen as this giant cloud that you go to by saying www.google.com, and computing resources are assigned to you as needed. Other enterprises, maybe some of yours, are on the net, but they are isolated from the public network by firewalls in order to protect the computing equipment that might be part of the business that are not necessarily able to defend themselves, or which you don't wish to be seen visibly except through a virtual private network. So when we get done counting laptops and desktops and servers hiding behind firewalls and mobiles, the number of internet-capable devices is probably on the order of 2 to 3 billion. Nobody knows how many for sure. In terms of the number of users, the mid-year estimate last year was 2.4 billion. By this time, it is probably closer to 2.7, 2.8 billion. And in terms of mobiles, there are 6.5 billion mobiles in use now all around the world. Not all of them are internet capable. Probably 20% have that capacity. So there's a substantial number of devices that are already on the net, and as you'll see in the course of this talk, there will be a substantially larger number of them coming as more and more appliances become internet capable. Now, if you're interested in doing business on the internet, you have to know where the people are. And at a company like Google, which is intending to do business literally in every country in the world, understanding the distribution of the users is important to us because it tells us what languages are going to be common, what interests are likely to be common, what kinds of cultural preferences are likely to be there, what kinds of local information would be useful for the consumers in each region. So statistics like this and more refined ones that are specifically country by country are very helpful for anyone who's planning to do business on the net. Now, if I were giving this talk 10 years ago, North America would have been the largest penetration on the internet. But now, as you see, Asia is the largest aggregation. About 500 to 550 million of the billion Asians that are online are from mainland China. And I think it's an important statistic to recognize that despite all of the issues associated with interference with free speech and a variety of other things, which we see every day as trying to do business in China, in spite of all of that, the Chinese are making a huge investment in internet infrastructure. Their CERNET, which is their education and research network, has been running full IPv6 for 4 or 5 years now, including network management. It's a tour de force implementation of IPv6. Now, you can also see that the average penetration in Asia is only 27%, so these numbers are going to get a lot bigger as the penetration rate goes up. Europe is now at 63% of the population online, but I've given up making any predictions about Europe because they keep adding countries, so the definition of Europe keeps changing. That makes it hard to predict anything. But it is the second largest region that's online on the net. North America comes next, and the others are as you see. If you move over to the statistics for India, I have to tell you I'm very disappointed in these numbers. And I'm disappointed not because the absolute numbers are relatively low, but rather for the harm that does to you and to your business opportunities and to opportunities for every citizen in the country. More internet access is going to be very beneficial. It improves all kinds of things, including access to educational material, which can be made available in very large quantities from many, many different sources. So the numbers that I have been given say that there are 300 million data-capable phones, but only 80 million have been actually turned on to run data. Part of the reason for this is expense, cost. So there's an issue there. Smartphones number 27.5 million. The average penetration then of internet in this country is only 11%. The Asian average is 27, so we're already well below the average. And I took the liberty of listing some of the other countries that are considered part of Asia. And some of the penetration rates are absolutely stunning. South Korea is at 82.5%. Singapore is at 75%. Hong Kong at nearly 75%. Malaysia at 60%. Armenia at 60%. Even Pakistan is at 15.3%. We have to do something about this. This is not an acceptable situation for any of you, especially if you plan to use internet as an avenue for doing business not only domestically, but also doing business on an international basis. So one of the questions that I've been asking myself and asking others is what can be done to increase the infrastructure and ability to access the network? What could be done to reduce the cost of getting access to the internet so more and more people can get online and take advantage of the system? Ramaraj has already mentioned two very important things at the top of the list here, and that's the introduction of IP version 6 into the internet address space. This is a kind of an embarrassing thing to admit, but when Bob Kahn and I were doing the original design in 1973, we didn't know how many terminations we should plan for in this network. First of all, it would have been arrogant for us to plan or imagine that this would become a global network. But we gave a little thought to this. He said, remember, this is 1973, so the kinds of computers that were available then were very large, very expensive mainframe computers that were time-shared. And so they served anywhere from 1,000 to 10,000 people. We had just finished building the ARPANET, which was a fairly expensive proposition, tens of millions of dollars to deploy the system across the U.S., and with relatively light penetration, academia and some military bases. It was still fairly expensive back then. So we said, well, all right, let's see, how many computers are really going to be needed in every country? And we guessed that 16 million machines would be more than enough per network, especially considering each machine might serve anywhere from 1,000 to 10,000 users. So that's 24 bits of address space. And then we said, how many countries are there? And there was no Google at the time to go find out the answer. So we guessed at 128, because programmers always think in terms of powers of 2. So that took 7 bits, and we thought there might be 2 networks per country, so there'd be a little bit of competition. So that's 256. So that's 8 more bits. So there's 32 bits of address space were estimated based on this very simple little calculation. Well, ironically, that actually lasted for quite some time. We turned the net on in January of '83. We didn't actually run out at the ICANN level of internet address space to hand out to the regional internet registries, in your case APNIC, until February of 2011. So that's not too bad, given it was an experiment. In fact, I thought what would happen is that if this was a successful experiment, that we would then re-engineer it in a production mode. The problem is the experiment got loose and out of control. We couldn't stop it, so it just took off. And so you've been running the experimental internet for the last 30 years, and only on June 6th of the last year did we formally turn on IPv6. We'd been testing it since 1996, but the internet service providers hadn't turned it on much. The edge devices have IPv6 in almost all the operating systems. The servers have it. Even the routers have it, but the ISPs haven't been turning it on. So I have a request of you. If you're using internet at all, please ask demand of your internet service provider, what is your IPv6 plan, and insist on getting an answer, because we've got to wake these people up to the fact that we have to have IPv6 in order to allow the network to grow, and you'll see why when we look at the near-term possibilities. Ramaraj has already mentioned the internationalized domain names, and they are a very important addition to domain name space, especially given that ICANN has now opened up the top-level domain space, which used to only have about 20 different top-level domains like .com and .net and .org. 2,000 applications were received for new top-level domains, and that's all being sorted out now because a number of companies propose the same name, so we have to sort out the competition. So that's a big change to the top-level domain space on the internet. There also are a number of initiatives underway in order to make more secure and more resistant to attack various parts of the internet infrastructure. The domain name system itself is now being populated with entries that have digital signatures on them. So when you do a lookup of the domain name and you get back an internet address response, you can ask for a signed answer that tells you that the pair has not been, that the response coming back has integrity and hasn't been modified by some attacker. The same kind of mechanism is being proposed for the routing system, which also has the vulnerability that someone can simply announce that they're using a certain part of the internet address space, and if everybody believes them, they've literally hijacked that space. We're going to stop them from doing that, again, using a public key capability. The other three bullets on here, some of you may not be able to see it, but they say sensor networks, smart grid, and mobile devices. And I will come back to all three of those momentarily, but I want to emphasize to you that what is happening to the internet is it's rapidly growing at the edges. Mobiles have been the first very visible addition to the network. And I guess I'd like to make a point to you, especially from the business point of view. I want you to think about these mobiles, smartphones, as devices that are programmable, plainly. They have power themselves. They're quite powerful computers. But the thing that makes them extraordinarily useful is that any one of those mobiles can get access to any resource on the internet and leverage it. And so the internet's resources of computers and the mobile's ability to get access to them is mutually reinforcing. And so the value of the mobile is dramatically higher because it can control, manage, and command access to information and computational power and applications on the internet service side. So together, these two things are really transforming the face of the net. But sensor networks and electrical appliances that are internet capable are also showing up. In fact, I've been watching, of course, for the last 40 years, the things that people have put up on the net, and I've been surprised. Picture frames. It never occurred to me that somebody would invent an internet-enabled picture frame which downloads images from websites and then cycles through them. So the grandparents are very happy about that because their sons and daughters take pictures of the grandchildren with their digital cameras. They upload these images to a website, and each of the picture frames in the family living room download those images and display them. So when the grandparents get up in the morning, they can see what their grandchildren have been up to for the week. Of course, there is a little issue because if the website that the picture frame is downloading images from has been hacked, the grandparents may see pictures of what they hope is not the grandchildren. So security now becomes an issue at home as well as at work. There are phones that look like phones, but they're actually voice-over IP computers. We have people, this one fellow from the Netherlands has invented an internet-enabled surfboard. I haven't met him, but I have a picture of him sitting on the water, waiting for the next wave, thinking, if I had a laptop and my surfboard, I could be surfing the internet while I'm waiting to get on the water. So he put a laptop in the surfboard and a Wi-Fi service at the rescue shack, and now he sells this as a product. So if you're interested in going surfing with internet capability in place, that's the product for you. I used to tell jokes that someday every light bulb would have an internet address, and I can't tell jokes about this anymore because somebody sent me an LED light bulb with an IPv6 radio in it running 6-LoWPAN. So it's a product. It costs about $20, maybe $15, and it only costs an extra 50 cents to put the IPv6 radio in it. So that's a small amount relative to the total cost. And the reason it's an expensive light bulb is it's LEDs, but they last for 15 or 20 years. So this is, in fact, quite a good investment. And it means it can be remotely controlled. You can test what the state of the light bulb is, turn it off and on. So we're seeing an increasing number of these kinds of internet-enabled devices, which is why you hear Internet of Things showing up a lot. Now, I mentioned sensor networks, and here's an example of one. I'm running an IPv6 6-LoWPAN radio network at home. Every one of these little devices is run off of two AA batteries. They last nearly a year. They are sampling temperature, humidity, and light levels in each room in the house, and every 5 minutes they send this information to a server that's down in my basement. Now, this is an ad hoc network that organizes itself. So these devices are actually store and forward relays in addition to being sensors. So the network connectivity changes as a function of local radio connectivity, possible interference and noise and things of that kind. So these devices accumulate this information for me, and I know only a geek would do this, but for me, at the end of the year, I have very, very good engineering data about how well the heating, ventilation, and air conditioning system worked, and I can now adjust the system based on real engineering data rather than on anecdotal results. Now, one room in the house is the wine cellar. Ramaraj mentioned that I'm a big wine fan. And so I care a lot about keeping that below 60 degrees Fahrenheit and also above about 40% humidity so the corks don't dry out. So that room has been alarmed, and if the temperature goes above 60 degrees Fahrenheit, I get an SMS on my mobile, which has happened a couple of times when I've been away, power has gone out, cooling system has stopped, and nobody is at home to reset it and turn it back on. So I called the people that make the system. Oh, by the way, this is a commercial product. This is not me in the garage with a soldering iron. It's called Archrock, a company that was acquired by Cisco a few years ago. So I called them up and I said, do you make remote actuators? And they said yes. And then I said, do you use strong authentication so that only the people I authorize can use the remote actuator, because there's a 15-year-old next door and I don't want him messing around with my wine cellar. So they said yes, and so we installed this over the weekend. And then I got to thinking that, I could actually tell if someone has gone into the wine cellar, even if I'm not there, because I can see that the light was turned off and on. But I don't know what they did in there. So it occurred to me that I could put an RFID chip on each wine bottle. And I could do an instantaneous inventory to find out if any bottles have left the wine cellar without my permission. And so I was proudly describing this design to one of my engineering friends, who promptly told me there was a bug in the design. And I said, what do you mean there's a bug? And he said, well, you could go into the wine cellar and drink the wine and leave the bottle. And so I wouldn't know the difference. So you have to put sensors in the cork. And if you're going to do that, you might as well sample the esters that make the wine taste the way it does. And before you open the bottle, you interrogate the cork to find out whether it's ready to drink. And if you discover that's the bottle that got up to 80 degrees Fahrenheit someday, you give that bottle to somebody who doesn't know the difference. So I'm finding this to be a very practical investment. But the point I want to make is that we are going to see more and more buildings instrumented like this. These kinds of devices can be used for security purposes. They can be used for environmental management. They can be used to evaluate the state of the residence or the business or office building. So this is going to become a very common thing on the internet, where you have at the edges sensor networks that are reporting conditions and responding to advice that you need to give to these various pieces of equipment. Now, I think it's also very important for you to appreciate that despite the fact that the internet design is 40 years old, and despite the fact that it's already undergoing quite a bit of change in the domain name space and the routing space and everything else, there are new technologies coming along all the time. So this is a very organic and very much evolving system. And when I'm speaking at universities, as I did today at IIT Madras, I wanted to emphasize to the students, and I want to emphasize to you, that the internet is not a static thing. It is dynamically adapting to new demands and new applications, and you and I can do that. We can make changes to the network. It's intended to allow people to do that. So one very fundamental example coming out of Stanford University is a new routing system called OpenFlow. And without getting down into a lot of details, all of the routers of the past have used only the address bits of each packet to figure out where the packets want to go. The OpenFlow guy said you can use any bits in the packet, including content, to decide in which direction to route the packets. And in fact, you could even use only content bits to decide where to route a packet. This is sort of like having somebody say, I'm interested in certain kinds of information, and radiate that into the routing tables. So the routing tables don't have addresses in them. They have indicators saying what you want to hear about. And when in a system like that, which is called content-centric routing, When a router receives a packet that says, "Hi, I am about architecture," it looks in the routing table and it sends copies of that packet to anybody that said, "I want to hear more about architecture." This is a complete departure from the conventional system. And OpenFlow, since it spans both spaces, you can use bits only from content, you can use a combination, or you can use bits only from address, means that it covers all conventional routing mechanisms and these new things. This is creating a new platform for exploring new ways of routing traffic in the net. Google has implemented OpenFlow in our data centers. And we did it because the centralized routing algorithm lets us allocate capacity on the data center network more effectively than conventional routing systems did. We get 95% efficiency on the optical fibers linking the data centers internally. And so we've been very happy with that. There are a variety of other things that are going on. Many of the issues associated with the net have to do with safety in the network. They have to do with attacks against the basic infrastructure or against the applications. And so there's work going on to improve the security and safety of the network. I mentioned DNSSEC, digital signatures on the domain name system. The certificate authority environment, which is supposed to validate the bona fides of a user of the net or a system on the net, has a serious problem because some of the certificate authorities have been compromised, and so they create certificates that are actually invalid and allow a perpetrator to appear to be Microsoft or Google or Apple or somebody else, and thereby persuade people to install software in their machines that they shouldn't be installing because the software looks valid because of this false certificate. So there are activities going on in the Internet Engineering Task Force to re-engineer the use of certificates for authentication using the domain name system itself as a platform to achieve that objective. Some of the attacks against the various infrastructure of the internet involve attacks against the routers, attacks against the operating systems of servers and laptops and so on, or attacks going through browsers, and that's the biggest hole in the internet today. If you think a little bit about how the World Wide Web works, a browser goes to a website after doing a domain name lookup to translate that into an IP address. It then downloads a file that's typically called the home file of a web page. It then interprets what's in the web file. In the early days of the World Wide Web, that file contained text, formatting information, and probably some imagery, and that's all. And so the browser was simply used that information to simply figure out how to lay out the page. But if you fast forward 20 years, you discover not only is there formatting information and text, there's also images, audio, and video, and also executable software or interpretable software. So Python, Java, and JavaScript, to name three high-level languages, are often downloaded into your machine, and the browser interprets that software. And in some cases, it's malware, it's badware, it's somebody's website has become infected. When you download the home page, the browser interprets the code, and the code stores something in your machine. It could store a virus or a worm or a Trojan horse or make a modification to the operating system. It's especially troublesome if the browser is operating at too high a level of privilege in the operating system and is allowed to store things where it shouldn't. So we have to defend against that by building better operating systems that are more resistant to attack and building browsers that are more paranoid about what they do with the information they've downloaded. Google's contribution to this is the Android operating system, the Chrome operating system, which is open source. It's available to anyone who wants to use it. It gets scrutinized by millions of programmers. And the Chrome browser, which is also open source and available to anyone who wants to use it. Those contributions are simply intended to help improve the quality of these various components of the edges of the internet, in part to make things more efficient and in part to resist some of the bad things that happen on the net. In the interest of time, I am not going to go into the rest of these bullets, but at least one or two of them will come up in another context momentarily. I wanted to turn now to business opportunities on the net. Now, I need to warn you, I'm a software engineer, right? So talking to a bunch of businessmen is, you get what you deserve, right, from an engineer who wouldn't know a business model if it jumped up and bit him on the nose. But I do see a variety of opportunities here. And in this country, you're certainly no stranger to information technology. You've figured out how to offer services outside of the domestic market. So when we think about Infosys and Wipro and others, you have already figured out that investment in infrastructure and in training and in businesses to serve others who are already heavily penetrated with internet is a good idea. And as you build up your own domestic market for IT, serving the rest of the world's market is a smart move, and it's been very good for a number of companies here in this country. So you're already figuring that part out. The thing which makes the internet go as an engine, in part, are standards and platforms, interoperability, and third-party applications. Google and other companies recognize that if you create a standard platform with standard application programming interfaces, you enable others to create new applications. So in the case of the Chrome browser and the Android operating system, many third parties have been able to invent applications for mobiles, and the standard application programming interfaces allow literally hundreds of thousands of individuals and companies to build these applications and make them available to everyone through an app store. The part that's interesting is that the standards mean that lots and lots of people can build the applications without worrying about how to deal with all of the underlying infrastructure that's already sitting there waiting for them. This is sort of like an enabling function that lets you worry about the application and not all the rest of the software that goes underneath. The same thing can be said for the Internet of Things. If you are, in fact, building devices, appliances like the ones that we joked about, the refrigerators and the picture frames, or other appliances that consume electricity, if you build standard interfaces to them, then third parties can manage them on behalf of others. So let's take an example, entertainment services. You have a variety of entertainment devices at home. You have large screen displays, you have digital video recorders, you have audio players and the like. Maybe you have iPods and things of that sort. You can imagine if all of those devices are on the internet, and if they all have a standard way of interacting, then a third party can come to you and say, I would like to offer to manage your entertainment for you. Go to this website, tell me which devices you have at home. I'll go figure out what their internet addresses are. And if you authorize me to do so, and then you go to a web page and say which movies you want to see and which music you want to listen to, I will take care of downloading things to the iPod, downloading things to the DVR, putting things in the car, and managing all of that on your behalf. So you only have to click on a few things on a web page in order to tell this third-party system what you want your entertainment system to do. There are lots of examples of that kind that are possible. Many of you know, of course, that cloud-based computing has become a big thing. It's physically important. Google's data centers are really big, and they have a lot of computing power in them. The same can be said for the Azure system from Microsoft or the private clouds that IBM makes, or for that matter, Amazon with its infrastructure. Standards, however, are not yet developed for the clouds. And although many of the cloud services are accessible through web-based interfaces, we don't have any mechanism right now to move data from one cloud to another. If we ever get to the point where we have standards to do that, there's another big opportunity for businesses to get into the business of managing information and information flows from one cloud to another. I can imagine a lot of clients deciding they want to put their information in Cloud A, and then they discover that Cloud B has some capability that Cloud A doesn't have, and they want to move a large quantity of information from Cloud A to Cloud B. Well, today's environment would allow you to download the information into your laptop or your desktop, but it wouldn't allow you to say to Cloud A, move this data to Cloud B. On top of that, if the data in Cloud A is access controlled, there's metadata associated with the information that you provided saying, please let only the following parties get access to this data. When you move the data to another cloud, you want to make sure the access control information gets there too. You need to have standards for expressing that access control, for saying which parties are allowed to get access to it and how can they establish their bona fides to do that. None of those standards exist right now. So the inter-cloud world is today in 2013 where the internet world was 40 years ago. There were networks, but they were proprietary. IBM had SNA, Digital had DECnet, HP had DS. You could build you could build a network of HP machines and a network of digital machines and a network of IBM machines, but you couldn't get them all to talk to each other. A non-proprietary standard was needed. That's where we are with intercloud today. So the research institutions in India, as well as others around the world, have an opportunity to contribute to making the clouds even more useful by building those kinds of standards or designing those kinds of standards. Another thing which has happened, which also may turn out to be very relevant to the situation here in India, is the emergence of massive open online courses that allow a large number of students to get access to high-quality lectures and examinations and the like. Two of my colleagues at Google are adjunct professors at Stanford, and earlier last year, just about a year ago, two of them decided that they wanted to teach an artificial intelligence class, but they wanted to offer it over the internet. So they guessed that maybe 500 people would sign up for this class, so they didn't really advertise it very much. 160,000 people signed up for the class. And of course, there's a brief gasp, and now what? A lot of software got rewritten to deal with the scale. Not very many weeks later, another class was organized that had 350,000 people signing up. Now, not everybody completed the class. In the 160,000 size class, about 23,000 people actually completed the course. But if you think for just a second about how long it would take you to teach 23,000 people that particular topic in a conventional classroom setting, you're talking decades. So in one step, in a few weeks' time, these two guys reached 23,000 people to complete the class. Well, we're seeing this over and over now, where internet is accessible at adequate rates so that video can be streamed, and so interaction is essentially real time. This is a big opportunity here in India, because if you can take the best lecturers and make their courses available to a large number of users, we can begin to increase the quality and quantity of people going for advanced degrees in computer science, and that has to be a good thing. But in order to get there, we have to have the infrastructure that will support these kinds of large-scale classes, which means investment in the private sector, and I think it means investment by the government or the states of India in order to make sure that this infrastructure is in place. And so this is an opportunity for cooperation and investment and collaboration among all the various interested parties to lift the level of academic capability in the country and lift the quality of education. It even allows you to get access to courses that are being taught outside of India that are easily reachable from other sources. So we are seeing both nonprofit and for-profit institutions beginning to form in the United States, and I presume we will see this happen in other countries, to offer this kind of large-scale environment. At Stanford, the president of the university, John Hennessy, has embraced this idea of the MOOCs, the massive open online courses, even though the business model for this is still not too clear. I mean, if you offer all the courseware for free, which is what's happened so far, then the question is, how do you maintain a big, expensive university plant? But in spite of the fact that this hasn't been worked out, John Hennessy is a big fan. And what's happened in the faculty is that some of them have completely inverted the way they teach classes. They record the videos, they let the students watch them as often and as many times as they want, and when they get into the classroom, they solve problems instead of the other way around. And so this potential transformation of the way people spend time in classrooms makes a big difference, because learning how to solve a problem, working your way through it, is the most powerful way of learning new material. It's one thing for people to tell you about it. It's something else to actually use this knowledge to solve a problem. And so I see this as a significant shift in our thinking about teaching at scale. And I've already harped about telecom and internet infrastructure. It's plain that we need more of it here in order to take advantage of some of these possibilities. There's also a program in the U.S. which is mirrored in some other countries. In Japan, this is called the Smart Neighborhood. In the U.S., we call it the Smart Grid. This is the introduction of internet-capable appliances that use electricity. And there are two motivations for this. The first one is to be able to tell an electricity-using device to not use electricity during a peak load. So if it's a water heater or a dishwasher or some other appliance that doesn't have a need for real-time immediate operation, it could be told, please delay using electrical power for the next 15 minutes because I'm hitting a peak load. Now the reason that's important is that if you look at peak load capacity, it's used only a few % of the time during the year. But you have to invest an enormous amount of money in the plant in order to have it available, even if it's only a few % of time during the year, which means that the price per kilowatt or cost per kilowatt hour is very, very high for that peak load plant. If you can clip the peak load, you don't have to make the investment in the extra generation capacity. So the ability to control demand, in addition to simply meeting demand, changes a significant equation in the cost of electrical power. There's a second reason for wanting to make these devices more intelligent, and that's so they can keep track of when they are being used and how much they are being used. And that information can be made available to the consumers so that the consumers can understand what is it that made up this electric bill at the end of the month. What did I do? What choices did I make that caused my bill to be this much? And are there changes that I could make in my behavior patterns or preferences that would reduce the power consumption? You can imagine third parties taking this data that's been analyzed or collected from the appliances and helping you figure out what to do differently. So this is an opportunity, again, for a third party to serve a consumer and help feedback to the users the way in which their lifestyle choices affect cost and affect demand for electricity. There are a number of issues associated with this kind of design, because now you start to get worried with appliances and power generation systems and everything else being online, that somebody will try to exploit access to that system in order to do harm. You can imagine if all of the air conditioners turned on at the same time and then were turned off and turned on and turned off, then in a conventional power generation and distribution system, you could have some really serious problems with the generators. So in the course of doing the smart grid work, there's a lot of attention being paid to security and resilience in order to protect against some of those bad sorts of hazards. I wanted to mention something down at the bottom here. The IEEE Spectrum magazine in this year's January issue had a most interesting brief article. It's very tantalizing. They said that that the Japanese researchers were developing a kind of, let me call it a power internet. They weren't quite getting to the point where they were packetizing the electrons and sending them around, but they came very close, because what they were doing is having a power router that got information like you would get from the routing algorithm saying what the demand was for power. The power generation was done in small size units. So they were literally building a network of networks, just like the internet, except for power generation. They were all interconnected, and power could be routed in any direction that demand was coming from. But because the power generation was kind of neighborhood size, and the whole system was loosely coupled, the cost of building any one of the power generation systems was not very high. And so instead of worrying about having to spend a huge amount of money on a giant power plant, you could spend less money, but for a larger number of these power plants, they would be more resilient in the case of various power failures or interference with or damage to the distribution system, because they'd be more dispersed. So I'm looking with great interest on the outcome of this particular Japanese experiment, because I think it might inform alternatives and choices for power distribution and generation here in India. So I think from the technical point of view, one of the things that has made the internet such a resilient system, one which has been so open to innovation, is first of all, the standards are readily available to anyone. In fact, at the very early stages of all this, when Bob Kahn and I wrote the first papers, we released all the information publicly. We made no intellectual property claims at all on how you build an internet. And frankly, what we were hoping is that people would take the papers, figure out how to build a piece of the internet, build a piece, and then find somebody to connect to, in which case the network would grow in a very organic way in the private sector, making decisions about which hardware and software to use, who to come to negotiate with to connect up a piece of the internet to another piece. That's exactly what's happened. And because we eschewed any kind of patent control or anything else, there were no barriers to people's adoption of this technology. And although it has taken rather a long time from our point of view to get where it is now, it has gotten there in part because everyone had access to the specific standards. Another thing is that the internet protocol design itself was meant to be a little on the stupid side. It doesn't have any idea how any of the packets are being transported. So it doesn't know if the packets are going over a satellite link or a mobile radio link or an optical fiber or something else, which meant that the internet packet layer of the system could be placed on top of any transmission and switching environment. And so Bob and I were imagining in 1973 that there would be new transmission and switching systems coming, like ATM and frame relay and things like that, or MPLS on the optical fibers. And we didn't want the internet to be foreclosed from using those new technologies. So we made a very stupid internet layer of protocol that had no idea either how it was being transported or even how it was being routed. If you actually look at the spec for the internet protocol, there's no mention of routing. This is a separate standard which takes place independent of the internet layer of protocol. And the routers run the background routing algorithms, of which there are many, which is another opportunity to compete. And then they decide how the packets are routed. The other thing about the packets is that they have no clue about what they're carrying. So the internet layer doesn't know what applications are using it, which means that it has been possible to put new applications on the net without making any change to the internet protocol. We also didn't have to go and get permission from every internet service provider in the world before a new application was put up on the net, because everything was done end-to-end. The network does not have any idea what application you're running, and it shouldn't know. This is what we call permissionless innovation. The network never knows that somebody has invented a new application, and I can guarantee you that Larry Page and Sergey Brin didn't go around to every ISP in the world when they decided to bring up Google. The same can be said for Amazon and for all the other major internet services. They just put them up on the net and let people discover them. There's also a very interesting aspect of business model that the internet has introduced. In the past, the way telecom was paid for is that the party that was making a phone call was responsible for paying everybody between the source and destination of that phone call. In the internet environment, each party that's on the edge of the net pays to get on the net. The networks in between figure out among themselves how they will deal with interconnection. Sometimes it's paid, sometimes it's not. And so the end result of all this is that we don't have settlement rates. And once you get onto the net, you can do, in theory, anything you want to do. Each party is already paid to get access to the network. The network is just carrying packets back and forth, and it doesn't know what is being done with them, because that's the job of software at the edge of the net, in the laptops and in the servers. So that's why you see a proliferation of applications coming, because nobody has to change the network in order to add a new application. Now that's a little bit of an overstatement, because in the earliest days of the internet, the backbone speed was 50 kilobits a second. That's a dial-up modem now. So you couldn't do quite all the things then that you can do today. Now we have 40 gigabit to 100 gigabit backbone. have gigabit to edge gigabit speeds like we have in Kansas City, a fiber network that Google is installing. When you have a gigabit per second end-to-end, there are things that you can do that you can't do when you have 50 kilobits a second. Although it was pretty amusing that even back in the mid-1970s, we were experimenting with packetized voice and we were experimenting with packetized video. It's just that we couldn't do very much of it. But we were very conscious of the Internet's potential to carry all forms of communication. Now we can do more of that than we could before. Intellectual property has turned out to be a big issue in the net, and Ramaraj mentioned PIPA and SOPA as legislation that would seriously have interfered with the security of the network, in fact, and the freedom of people to express themselves and get access to content. But we all recognize that there are reasons for some people to want to not have copies of their content distributed by third parties without permission. So in considering intellectual property, at least in the, within the context of the Berne Convention, which the U.S. adopted in 1976, that convention says if you create a work, it's instantly yours. It is instantly copyright. You don't have to register somewhere in order to get the benefit of ownership of the content that you've created. The problem here is that not everybody who creates content wants to treat it as full copyright material. Some people want to give it away. That's what happened with the World Wide Web. In the early stages, everybody put information on the net, didn't expect to be compensated, but they were pleased if somebody else looked and found it useful. And that's still true today. So there is a range of potential treatments for information that people create, and a lot of it is not pure copyright. So a man named Larry Lessig created a notion called Creative Commons, which gives you a full spectrum of choices. You can use the full power of intellectual property control, standard copyright, or you can go all the way to the other side of public domain or someplace in between. And so using Creative Commons as opposed to conventional copyright allows for a much richer palette for deciding how to treat intellectual property. Now, Ramaraj mentioned that we are facing a lot of policy challenges today. There was a conference that was held, an intergovernmental conference that was held starting in 2003 and again in 2005, and it was called the World Summit on the Information Society. And this is a bunch of bureaucrats. I hope I haven't insulted anybody here, but a bunch of bureaucrats were showing up trying to figure out what's an information society. And so somebody said, well, the internet looks like an information society. Immediately, these bureaucrats said, well, who's in charge of the internet? And we said, well, nobody. It's a fully distributed system. It's a multi-stakeholder environment. They wouldn't believe us. They said that somebody has to be in charge of a system on this scale. Then they noticed ICANN. It's the only place where there is some centralizing of management, because we want to hand out internet addresses in such a way that we don't give the same address to two different people. And the same is true for the domain names. You want to assign them so that only one party has authority to use that domain name. So there is some centralization for purposes of assuring that you have uniqueness, and that's all that ICANN does. And it hands these things out in such a way that this is a hierarchical structure. So ICANN hands out top-level domains to parties who then allow registration of second-level domains, and the parties who have the second-level domains can create third-level and fourth-level domains if they wish. The same thing is true for internet address space. It's handed out by ICANN to regional internet registries, APNIC in your case, and the regional internet registries in turn hand out internet address to the internet service providers, who themselves provide addresses to end users. So this is a highly distributed hierarchical system. It's very hard for many governments to appreciate that this kind of thing can actually work in such a distributed way. The International Telecommunications Union was the sponsor of this first World Summit on the Information Society. And in the course of this big debate about who's in charge of the internet, since nobody could make up their mind, one of the institutions that came out of this WSIS thing was the Internet Governance Forum, which was formed, as was ICANN, in a multi-stakeholder way. So the private sector, that's you and me, civil society, the technical community, and governments were all allowed to sit at the table as equals to talk about policy and policy issues arising from the use of the internet. So there are a continuing series of meetings, many of which are intergovernmental, driven by the ITU, in which debates over who's in charge of the internet and what can they do or what can they not do. The most recent of which was the World Conference on International Telecommunications held in Dubai in December. And during the course of that meeting, a lot of proposals were made which would destroy the very essence of what makes the internet open. Some people wanted to reintroduce settlement rates and caller pays kinds of models. Some people wanted to formally introduce censorship on the system. Some others wanted to enforce interconnection regimes instead of allowing the kind of very free-flowing pairwise bilateral negotiations. Fortunately, most of those extreme proposals were not adopted, and as you heard earlier, Minister Sipal was brilliantly articulate at the Internet Governance Forum and later the World Conference on International Telecom, rejecting a lot of those extreme positions in preference to opening up and making the internet as freely accessible as possible. We still do face problems on the network, and one of the things which I think is the most important to recognize is that there are real harms that occur to people on the network, whether it's viruses and worms, Trojan horses, or stalking, or other kinds of attacks against the users of the net. So that means we should be paying more attention to safety. We should be building more technical tools in to protect people from harm while we're also trying to protect the freedom of their expression. There's work to be done technically, there's work to be done from a policy point of view, and there's work to be done from the social point of view. And the problem that we have is that you and I have cameras in our mobiles. We take pictures, we upload them into the net. Those pictures are often of people that didn't know they were being photographed, and you didn't care. You were trying to take a picture of a building somewhere. They just happened to get caught in the photograph. And we post this, and in some cases this proves to be a real invasion of privacy, because the picture you took of somebody, which is given a date, time, and location, might expose that person as having been at a place where that person said they weren't. And so, we harm each other accidentally by these innocent actions. So we are going to have to figure out what kind of social norms make sense in this online environment, and we haven't figured this out yet. I think we're going to have to stumble around, and some harms will occur, and we'll have to figure out collectively and internationally what social graces should be applied in the online environment. Now, there's much more to be said, but I'm not going to say it. I'm already about 7 minutes over what I had intended. But I would like to ask permission to give you an update on one other project called the Interplanetary Internet, to give you a sense for what the future is already going to be like. In 1998, the year that ICANN was formed, and the year that Google was formed, some of my colleagues and I at the Jet Propulsion Laboratory were asking ourselves, okay, it's been about 25 years since the internet was designed. What should we be doing now, that is to say in 1998, that is going to be needed in 25 years' time? And the answer we came up with was interplanetary communications that has the same richness of the internet. And part of this was driven by the exploration of Mars. As you'll remember, there were 2 Viking landers in 1976 successfully delivered information back, and then there was a period of very bad failures. And then in 1997, a little Pathfinder robot was landed successfully. And then in 2004, there were 2 rovers that landed in January. And then more recently, in 2008, in the upper right-hand corner, a Phoenix mission landed at the North Pole of Mars, and then finally in August of last year, the Mars Science Laboratory, it's about the size of a small automobile, landed successfully, and it's delivering data back. Now, we started out thinking, okay, let's see, TCP/IP, it works okay on Earth, so it ought to work on Mars. And I think that's actually true. It will work just fine on Mars. But as we thought more about this, we realized that it would not work between the planets. And the reason for this is that the speed of light is too slow, and we haven't figured out how to fix that. So, we didn't want to get Einstein mad at us. So we said, gee, this is a problem, isn't it? Because the planets are in motion, and when Earth is closest to Mars, it's still 35 million miles. That's 3.5 minutes for one-way radio signal. And when they're farthest apart, it's 235 million miles. That's 20 minutes one way. I can guarantee you that the TCP protocol's flow control system was not designed for a 40-minute round-trip time, and it only gets worse when you get to the outer planets. Then there's this other problem. It's called celestial motion, and the planets are rotating, and we haven't figured out how to stop that either. So if there's something on the surface that you're trying to talk to and the planet rotates, you have to wait till it comes back around again so you can talk to it. So we have variable delay and we have disruption. TCP/IP is wonderful when you have high connectivity, low error rates, and high speeds. That's not what we have in interplanetary communication. So we sat down and said, all right, we have to design a whole new suite of protocols that are delay and disruption tolerant. We call these DTN protocols. The particular one we're using is called the bundle protocol, and it is on board the International Space Station. It's on board 2 of the orbiters around Mars. It's on board the rovers and the Mars Science Lander. It was on board the Phoenix lander in the North Pole of Mars, but that sort of died during the winter. It's also on board a spacecraft that's in orbit around the Sun called Epoxy, which has visited 2 comets so far. So we are literally already on our way with a 2-planet interplanetary network between Earth and Mars. And what we are now doing is standardizing the new protocols in order to allow every spacecraft launched by every spacefaring nation to have this commonality. So either during the mission, primary mission, they can use each other's communications for relays, just like when we plug into the internet, we can talk to 900 million machines, or when a spacecraft's primary mission has completed and the spacecraft is still operational, we can turn it into a relay to become part of a store and forward interplanetary backbone. So we're anticipating standardizing this through the Consultative Committee on Space Data Systems, and over time we expect to see literally an interplanetary backbone grow mission by mission. We're not trying to build one giant network all at once and then hope that somebody will come and use it. The idea is to build it as the missions are justified and can be paid for. Well, the story doesn't end there, because last year the Defense Advanced Research Projects Agency, DARPA again, just awarded a contract to a little consortium, and I'm a small part of that, to design a spacecraft that can get to the nearest star, 4.4 light years away, in 100 elapsed years. Well, we have some problems to overcome to actually do that, because the current propulsion systems that are available would take 65,000 years to get to the nearest star. That's a little long even for a DARPA project. It's 6 times longer than our civilization has been in existence. So it's possible that we won't be in existence by the time the spacecraft gets to the other end. So we need a very much more powerful propulsion system. Our estimate is we need to get up to 20% the speed of light at the halfway point at 50 years, because we need to turn over and slow down, because otherwise when we go through the system we'll get 1 photograph, and that's very expensive. So we want to go into orbit around Alpha Centauri or Beta Centauri. So that problem is likely to be solved with high-power ion engines, of which there are several now to choose from. There's another problem for us is navigation. And when you think about it, astronomy is one big fake, because the stars aren't where they look like. We're seeing them in the past, right, because of the time it takes for the light to get to us. So you can't aim for a star and expect to get there, because it isn't there. It's someplace else by this time. So I got worried about navigation, thinking, well, what happens if the spacecraft gets about 1 light year away and you want to tell it to do a mid-course correction? It takes a year for the signal to get there and another year for you to find out what happened. So we have to really rely on autonomous navigation. By good fortune, we actually know something about the proper motion of stars that are in our nearby system within 10 light years or so. So we can actually put autonomous navigation on the spacecraft, and it can look at stars that are much farther away that will not appear to have moved much in order to orient themselves. Then they can do their own mid-course correction to get to, in this case, Alpha Centauri system. Then there's one other little problem, the one that I'm most interested in, that's signaling. How do you generate a signal that can be picked up from 4 light years away? Now remember, we don't have a nuclear bomb that we're sending with it to make one big pulse. You get one bit of information, I'm here, and that's all you get. We'd like to get a little more than that. So we're thinking about using lasers, which will give us fairly high speed. We probably will use a femtosecond laser, which means the pulses are 10 to the minus 15 seconds. If you got 100 watts of power available, when you compress it down to 10 to the minus 15 seconds, it's a big pulse. So you should be able to detect that from quite a distance away. The trouble is that the light beam spreads. Even though it's a collimated laser, by the time it gets to the solar system, it has spread to about the size of the solar system. So it's a very weak signal, which now you know why I need the interplanetary backbone. I have to build a big synthetic aperture receiver the size of the solar system in order to detect the signal coming back from Alpha Centauri. But one of the researchers has pointed out to us that Einstein showed that gravity bends light. If you remember an experiment around 1916 or something like that, when there was an eclipse of the sun, and you could see that the starlight from a star had bent a little bit because of the effect of the sun's gravity. Well, if you extrapolate that a little bit, you realize that if you could get a spacecraft to 550 astronomical units away from the sun, and AU is 93 million miles, the distance between Earth and the sun. If you can get 550 astronomical units away from the sun, you're at the beginning of the focal plane of the sun's gravitational lens. So, and that still is relatively focused all the way to 1,000 AU out. So if we could send a spacecraft to the right place, 550 AU away from the sun, we could focus the light coming from that femtosecond laser. And we don't have to build the entire interplanetary backbone with a synthetic aperture receiver. We just sit there and let the sun do the work for us. So that's the sort of speculative plan that we're working on now. I probably won't be around by the time this thing gets launched, but I can tell you that in spite of that, it's still like living in a science fiction story, because you're talking seriously about getting to another star, signaling information back, wondering how to keep the system alive for 100 years or more. When it's hard to keep some satellites in orbit for 18 months. So that's the up-to-the-date report on the interplanetary network. I realize I've gone on for about 15 minutes more than I intended, and I apologize for that. I'm happy to stick around and answer questions if you have them, and then I'm given to understand there's some refreshments after that. So thank you very much for your time tonight. I'm happy to answer questions, and I look forward to seeing you again next year. Thank you.
Thank you, Dr. Cerf. Open for questions. Yes, Jiten, could we have you around?
Yeah, my name is Ram Kumar. So my question is, basically it's about cost.
Yes.
See, in the US, if you compare by purchasing power parity or as a percentage of income, as of today, whatever is the tariff available for a broadband connection at home,
yes,
through wire, there is almost 1:100 per GB cost if you compare. I get $25, 250 GB per month. Here, no, it's almost 100 times more if I include the purchasing power parity.
Yeah.
So is it really a technological problem, or is it more of a economics problem?
So, well, it's clearly economics is an issue here, and there's no question that cost is always an important barrier to try to reduce. It would be, two things have occurred to me. Some countries, not the US, have chosen to make a national investment in infrastructure. Australia and New Zealand are the primary examples. They've decided to use government resources to build the basic fiber infrastructure in both countries. This is not inexpensive. They are taxing themselves to do it. On the other hand, they see this as a national investment for the long term. Once that fiber has been pulled, the electronics that go with it can be changed over time as new technology comes and higher speeds are available. So that's one solution that Australia chose to introduce. A lot of the cost of putting in facilities is labor cost. And so in theory, this should be advantageous for India because the labor costs are lower here than they are in other places. So one possibility is that even if it's the private sector, assisted perhaps by low interest loans or other things, could possibly participate in creating the physical infrastructure at a reasonable cost. There are municipalities in the United States and in other countries that decide to tax themselves in order to build fiber infrastructure. Google has chosen to do something different. We had two questions, actually. One of them was to try to understand ourselves what the economics of high-speed networking really were. In this particular case, we're building a gigabit network in Kansas City on both sides of the river, Kansas City, Kansas, and Kansas City, Missouri, partly to find out what will people do if, am I starting to sound scratchy, or is this the vodka that I asked for? Which will make the whole meeting more amusing for me, if not for you. Thank you. So in that particular case, we wanted to see what would happen if people had access to such high speed. Here's a small little tidbit. If you have a gigabit per second available, you can download an hour's worth of video in 15 seconds. This changes the notion of video on demand. Today, it usually means streaming video. This is faster than you can watch it. And so what do? You download it and play it back. The consequences of that are interesting because it's less of a challenge to the network to do a file transfer than it is to deliver streaming video. The obvious reason is that the streaming video has to get there at exactly the right time. Audio and video have to stay in sync. If it's a file transfer, it doesn't even care if you lost a packet. It transmits the packet, and you play it all back after you've downloaded it. So that's one reason that we're interested in doing this. The second one is we weren't sure whether we believed the claims of the other broadband providers, typically telcos and cable companies, about the cost of actually doing this. So we thought, well, one way to find out is to go do it. So at some point, I hope that we are able to share what those costs actually turned out to be. Even if we don't, we are hoping to run this as a business. This is not intended to be a giveaway. And so far, we're beginning operation now. And one of the tactics that made a big difference was to offer to the residents that if they were willing to sign up for the service now, as we were deploying, that we would offer free service for a period of time. I forget how long, but it was at least 2 or 3 years, in order to make efficient the installation of the system. Because if you hook a house up while you're rolling out the fiber, it's so much less expensive than having somebody call you up a year and a half later and having a truck roll out to install the electro-optics and everything else. So lots of people signed up that way, and once you get past about 40% penetration, you are in the sweet spot, and quite a bit more than 40% actually signed up. So I think the solutions for getting infrastructure in place are varied and they will vary from country to country depending on local conditions. I rather like the idea of municipalities deciding to build their own local networks. I'm sorry to say that the telcos in the U.S. don't like this idea because they think it's competition and they don't like competition. And so they claim that it's competition by a government entity, the municipality, against the private sector. I think this is a misrepresentation because you know what would happen. The citizens of the city say, we want to tax ourselves, we'll float a bond, we will pay for this over time with taxes in order to cover the cost of capital and operational cost. And what the city will do with that bond is contract with the private sector to build the network. And so it's really a private sector initiative. It's just that the telco may not be the one that wins the contract, and they don't like that part. So I'm sorry if I've insulted any telcos in the room, but it was on purpose. So, well, you know, monopolies tend not to like competition because they have nowhere to go but down in terms of market share. So I hope that you find some solutions. Maybe more than one kind of solution will work. Maybe some states will choose to implement themselves. Some will encourage municipalities to do this. Maybe the national government will come together and decide to make a national level investment. One thing that could be done that would be very, very helpful is to build internet exchange points to link small internet service providers together, because that's very, very efficient to do that, and it's not very expensive to build an internet exchange point. So those are some of my reactions to the current state of affairs, and I hope we find a way forward here in India, because you really will benefit from having more higher speed internet available to everyone at a cost that you can afford. Okay, other questions?
Check. Yes, I'm David. My question comes from the Google logo on every single slide that you had. I was wondering if this was your viewpoint, or was this a consensus from the domain that you work in? And can we expect some diametrically opposite viewpoints from other evangelists, say from Microsoft or Yahoo?
I mean, from my point of view of openness on the network and freedom of expression and everything, I think that on the whole, the private sector, except even the telcos with whom we have other debates, were very much in favor during this World Conference on International Telecom of keeping the network as open as possible. We've had some debates in the U.S. over something called network neutrality. And in the course of those debates, the telcos and cable companies tended to line up against what they claimed was network neutrality. And I think it was a distortion of the real, there's a distortion field around some of those companies. What I had wanted to do, and what I think my colleagues wanted, not just at Google but others, was to assure that if you were in control of a broadband pipe that was delivering internet and other services to a consumer, that you couldn't use the fact that you were controlling the broadband internet access to interfere with other people who were trying to compete with you using that internet pipe. So a trivial example of this would be a cable company that is selling to the consumers video subscriptions to entertainment video, and also selling to them access to internet. And I'm not accusing anyone of anything, but I am suggesting that there would be a great temptation to notice that the competitors of your video service are using the internet channel in order to deliver this service to the consumers, and that if you just kind of messed up the packets a little bit on the internet and made the video not work very well, and you could do this in some very subtle way, then you would force the users off to use the conventional service offered by this broadband provider. That's anti-competitive, and that's the only thing that I've ever worried about. The debates that took place had people saying, Vint Cerf wants every packet to be treated exactly the same. No, actually, I wanted to have the low delay, video gaming stuff get priority, but I didn't want any particular company's game to be better than the others. I wanted all video games to get low latency service. And if it was streaming video, I didn't care where it was coming from. I wanted the streaming video application to get the kind of bandwidth that it needed. And there were also claims that I didn't want them to charge more for more usage. No, that's not true either. We recognize that if you use more capacity, you should pay for that. I did object to caps. And the reason I objected to caps is that those were measured on a monthly basis. And they would say if you send more than 5 gigabytes during the course of the month, then we will charge you a premium. My concern is that the real capacity limit had to do with bits per second, not with how much data did you send. If you sent a terabyte of data over the course of a month, averaged over the month, nobody would notice. If you send a terabyte of data in 15 seconds, everybody would notice because you'd be hogging the capacity. But the real issue was bits per second, and so the idea I've always thought was appropriate is that if you're trying to make sure that everyone has reasonable and fair access to the underlying capacity, if they ordered up, let's say one party ordered a 10 megabit service and another one ordered a 20 megabit service, while the system is uncongested, then almost everybody can get whatever data they need at whatever rate the maximum rate the system will deliver. If the system has become congested, at that point you have to put in access controls and flow controls to say that parties will get bandwidth in accordance with how much they are paying. They might not actually get the 20 megabits a second. The 20 megabit guy might only get 10, and the 10 megabit guy might only get 5, but they're getting a proportionate share of what they're paying. That's fair allocation under conditions of congestion. That's really all that I've ever argued for. And it's absolutely feasible to implement that kind of regime. So I don't know how this is going to come out in the United States. There are some court battles over whether the Federal Communications Commission can actually insist on this kind of neutrality. And we'll see how that works out. I hope that you guys do better here than we've done in the U.S. Okay, other questions?
We've got time for 2 more questions.
Okay.
Starting with JK right here.
Yes, sir.
Krishnan is my name. We are more comfortable talking to each other than writing or reading. So when do you think the default input-output on the internet would be voice?
So that's a very interesting question. Google has been experimenting with and offering voice interaction for quite some time now. We've offered it especially on mobiles because we'd like you not to be trying to text while you're driving or something else. So we accept voice in almost every situation where you would be typing. This is also true of the laptop. You may have to click on a microphone to tell it, please listen, but at that point it will attempt to correctly recognize speech. We do both sides of the equation. We will produce artificial speech from text. And so if you wanted, for example, to have turn-by-turn directions in the Google map system, you can ask for that, and it will try to talk you through how to get from where you are to where you want to go. It's a little harder to deal with generalized speech. If you've ever dealt with a speech response system on the telephone, it can be a very frustrating experience. You say something and it says, I don't understand. And then you start screaming, you bloody idiot, what's the matter with you? So one thing that we can say is that if the interaction has a confined vocabulary, we can actually do a pretty good job of recognizing what's coming because we can predict what might likely be said. So if you're talking to an airline reservation system and it says, what city do you want to go to? Theoretically, your response should be something like the name of a city. And so that reduces the possible things that it has to discriminate. Of course, if you say, you ought to know, you're my travel advisor, it will say, I don't understand, there is no city by that name. But the possibility of confining an exchange at each step in the exchange actually makes for a fairly powerful tool. The total vocabulary over the course of the exchange might be quite rich, but as long as any moment in it has a narrow vocabulary, the system can work pretty well. We've also experimented on YouTube with attempting to translate English into text, so automatic captions. Now, I have to tell you that the results are sometimes very amusing. Remember that they're very phonetic. And one of the funny examples was that someone was saying, and with this product, we will give you a free sample. And the way the speech system transcribed this was, with this product, we will give you a free salmon. And, I thought that was a fishy offer. But the result is that when, in the case of YouTube, if you upload a video that you've made, so you're the party who owns it, we will create a transcript with the timing track that says this utterance began at this time and it ended at this time, plus whatever our mistaken transcription is. You can download that and edit it. And I do this for a lot of my videos now. I'll do a little short 5-minute video. I will take the transcript, which has mistakes in it, download it, correct the transcript, and upload it again. And because the timing track is already there, The change to the words is actually quite easy. It takes half the time that it would to do captioning in the conventional way. Now, you raise a question which I would like to open up just a little bit. One of the things that we're experimenting with at Google is called Google Glass. These are a pair of glasses that you put on. There's a video display, which you can see up this direction, looking outside of the normal field of view. It has a video recorder, audio recorder, and it has this projection capability that you can see, and you can wear a headset so the system can produce sound as well. The idea here is that the computer has just been put down in the same sensory environment that you're in. So it can see what you see, and it can hear what you hear, and it can see you make gestures, and it can interpret that, and you can build a machine learning system in to understand your particular form of gesture as opposed to someone else's. We believe that as we let computers participate in the same sensory world that we're in, that our ability to interact and communicate will become much more comfortable and more natural than having to type on a keyboard or move a mouse around. But we're still in the process of evolving that. We have one more time for one more question. Somebody way in the back
Yes.
there. Okay, yes, sir.
My name is Arun.
Hello, my name is Vint.
Yes, sir. Didn't catch you? I would like to address the issue of standards compliance on the web, sir. So we have bodies like w3c.org. But what we do see is that the major corporations systematically ignore the standards. Microsoft, Oracle, Apple.
Mm-hmm.
What mechanism would you suggest? I mean, I would like your opinion on how do we thwart these attempts at walled gardens?
So pretending, if I've understood the question correctly, I would infer from that question that you would agree that non-proprietary standards are preferable to proprietary standards, but that proprietary standards often find their way into de facto use. And I would like to respond to that question if I've got your question correctly. There are several things that can be done and are being done to promote non-proprietary standards. One way to do that is to release software in open source form, and we do that at Google deliberately. Another, and that means anyone can make use of and can alter, if they wish, the software that's made available. The Internet Engineering Task Force is a very interesting example of a place where non-proprietary standards emerge. It's a very peculiar institution. It's housed in the Internet Society, but you can't join the IETF. There's no place to become a member. All you can do is show up and participate. And so that's what people do. And in fact, we've even had situations where there's some participants in the IETF who've never been to a face-to-face meeting. And the reason that's worked is that all the final decisions for all the protocols get made online at the end. There is a last call on the net, and anyone with an issue can raise that issue, and it has to be resolved by the area directors that are overseeing the Internet Engineering Task Force work. So I think that there is great power in non-proprietary standards. In the IETF, there is preference for standards that don't have patents associated with them. In some sense, it's inescapable that some hardware may be patented, but many of us are very uncomfortable with software patents, and it's becoming increasingly clear that patenting of software and various other kinds of user interfaces and things like that have led to extraordinary expense and delay for a lot of companies suing each other for patent infringement. My personal opinion, not Google's necessarily, but my personal opinion is that software patents were a mistake. And I wish that we would rethink that, because so many patents are granted for things that any CS 101 student knows is well known and well understood, but the patent examiner doesn't know that and issues a patent. So I think all we can do is collectively participate in standards making activities that emphasize non-proprietary standards, and try very hard not to adopt standards that have dependency on proprietary and patented content,
because you always get into this question of, even if it's fair and reasonable terms and conditions, who gets to decide what's fair and reasonable? The patent holder. So I would prefer to have no patents associated with non-proprietary standards. Well, I gather that's all the time we have, but we can have some informal interaction over refreshments, so I look forward to that. Thank you again very much.
Thank you, Dr. Cerf. I'd like to invite Vishy Viswanathan, Executive Director of TiE Chennai, to deliver the vote of thanks.
Wow, what a fascinating evening. I don't think I can find words to adequately describe how I feel. It's been, I think we are ready for the next session. But I think it's been like being with a rock star. And I was there yesterday at IIT, again, similar kind of feelings there also. So thank you very much, Dr. Cerf, for sparing your time and being with us. And it's been a while since we had a technical session. I don't think this was a purely technical session, but just shows the interest levels in Chennai and in TiE Chennai especially. So we hope that you can make it a point to visit Chennai often, at least once a year, and then we could have this as an annual feature, I guess. Anyway, thanks a lot. I also want to thank Shiva from Internet Society of India, Chennai chapter. And it was he who's alerted me that Dr. Cerf is going to be in town and suggested that we do a joint event. And I'm glad we seized that opportunity and then did this. So thank you so much, Shiva. And I also want to thank NASSCOM. Is Puru there? Yeah, thanks, Puru, for your partnership. And finally, thanks to each and every one of you who's here. Those of you who are not members of TiE and want to know more about TiE, please contact me, Lata. There's more information available at the registration desk. So as it always happens in typical TiE events, the second half is equally important as the first half. And this is where the networking takes place, and there is dinner, and also we have some wine as well. So we will now break for that, and before that, as a token of our affection and respect for Dr. Cerf, we'd like to present some mementos. Lakshmi.